Oh, okay. Okay. Well, we begin with lecture number 4 on two-dimensional homo-correlation spectroscopy, which is also very popularly known as COSY, correlation spectroscopy as COSY. This is a interesting topic because it involves transfer of magnetization from one spin to another. Transfer of magnetization, or we will often use the term coherence transfer. That is, the transfer of coherence of one spin is transferred to another spin. The word magnetization and coherence can be interchangeably used so long as we are talking about coherences of order 1. That is, coherence between eigenstates which differ in their total magnetic number by plus minus 1. But when we have coherences of order other than 1, then they're not relatable to magnetization. We will see the relationship of this coherence to magnetization in the chapter on multiple quantum transition spectroscopy a little more in detail. But for this lecture, it is sufficient that we think about a magnetization transfer. But what we really do in a one-dimensional, in a time domain NMR experiment is really look at coherence and not at a transition. And therefore, the word coherence is more appropriate in many circumstances. The interesting part of this lecture, or this part of the COSY, is that we are going to be doing coherence transfer. No such thing really existed in CW spectroscopy. And it's only in pulse spectroscopy that we could think about transfer of magnetization from one spin to another. Indeed, there were even in one-dimensional Fourier transform spectroscopy, one didn't think of really a coherence transfer till two-dimensional NMR spectroscopy came up. Therefore, it's a very special feature of two-dimensional NMR spectroscopy. Also, this is also the most powerful part of the two-dimensional spectroscopy, in which we transfer magnetization from one spin to another. And that is why I think this is an interesting lecture from that point of view. What we are going to concentrate, as I said before also, is on the transfer from the coherent coupling. That means that either the spins are J-coupled or they are dipolar coupled in a way that the dipolar splittings can be seen in the spectrum. The basic experiment of COSY, or two-dimensional correlated spectroscopy, is the one that was given by Genet in 71 and is the two-pulse experiment. And this, as I said before, is the most powerful of the 2D experiments. And the most important concept in that is that of the coherence transfer, or magnetization transfer, if you would like to call it like that. Let us see what is happening in this experiment. When we put the first pulse and then we excite magnetization or coherences of order 1, all single quantum coherences are excited. And they then evolve during the period T1 with their characteristic frequency. Let's call them A, B, C, D, and etc. Then after some time, after time T1, we apply a second pulse, and these coherences then either get transformed to other coherences, or these magnetization get transformed to other magnetization, or they remain the same. And again, they, in the time domain T2, they are detected. And if, for example, the frequency A had remained as a frequency A, and I did a two-dimensional Fourier transform and look at that data, then in a two-dimensional picture, it will appear has the same frequency in omega 1, would have the same frequency in omega 2, and therefore would appear as a diagonal peak. And B magnetization has a frequency B in omega 1, has a frequency B in omega 2, and therefore appears as a diagonal peak. But the interesting part of those is this, that magnetization, for example, A, which was a frequency A in time domain T1, becomes some other frequency, for example, a frequency D. Then you see in omega 1, it will have a frequency coordinate which is given by A. In the omega 2 domain, it will have a frequency coordinate which is D, and will appear as a cross peak, indicating that A resonance or A magnetization and demagnetization are somehow related to each other. Perhaps A resonance and D resonance are J-coupled. And this is happening for the entire spectrum. There is no selectivity here. This is a non-selective excitation, non-selective perturbation, and so this diagonal and cross peaks are taking place all over the spectrum, and so we get essentially a totality of information. And this is why it's a very powerful experiment. Now the basic important point here is the transfer of magnetization from one spin to another. This transfer is something that we should understand in detail before we go further. And there are several ways one can try to understand this transfer of magnetization. And I'm going to devote almost half of today's lecture just to understand as to how the transfer takes place, how we can interpret it, how we can understand it, the transfer of magnetization from one spin to another. The simplest is to write it up phenomenologically. So we draw a vector diagram and describe it phenomenologically, in the sense that, well, we have Z magnetization to begin with. We apply a 90-degree pulse. We'll put it in XY plane. I'm not very careful with the X and Y coordinates. Sometimes it's X, sometimes it's Y. Please bear with me. And so the magnetization has come in the XY plane, and then it precesses in the XY plane. And we can write down that precession as a frequency, a magnetization of a spin A, which has a cos omega A T1 plus I sine omega A T1. At the end of T1, we apply a pulse and throw away the sine component. So we are left with the cosine part of it. And then it again evolves with a frequency omega B, let us say, after the second pulse. And we just write it down as cos omega B T2 sine omega B T2. And then suppose we retain only the Y component of this total signal, then we have cos omega A cos omega B T2. And this gives us what we call as the amplitude modulated signal, amplitude modulated with respect to T1, and yields a pure phase 2D spectrum. Of course, the idea of coherence transfer or transfer of magnetization from one spin to another, we have put ad hoc here. We haven't really got it in how did this frequency A became B is not explained at all. We just wrote it down that it was A before and B later. But how did it become A to B is not clear from this picture. The other picture, which is the vector diagram picture, that was cos and sine picture, is slightly more illustrative. Okay, let us think about that. We have, suppose we have the magnetization of spin A in the Z direction to begin with, and then we apply a 90-degree pulse along the x-axis, and the magnetization comes to the Y direction, and it starts precessing. But before it starts precessing, I should look at this magnetization a little more carefully. The magnetization of spin A is built up of two components. And the spectrum of A would look like a doublet if it is coupled to a spin X. And these two doublets have the splitting which is equal to the coupling constant. And this is necessary before we can transfer magnetization from spin A to another spin. Also, there is one more interesting thing, that one can assign the spin state of the spin B, which is coupled to A, as to B is in plus state or minus the state. Okay, this one of the two lines belongs to this B up spin state, and the other line belongs to the B down spin state. Okay, therefore we can say that this magnetization consists of two terms, one which has a minus half J frequency of precession, another which has a plus half J of precession in the rotating frame exactly at the middle of these two, which the rotating frame frequency is the middle of this doublet. And then in that case, for example, the blue component is going by minus half J and the green component is going by plus half J. Suppose at the end of T1, the state of the spin system is such that these vectors are facing plus x direction and minus x direction. If not, it's only the component that we are thinking about which is in the plus x direction or the minus x direction. It is sufficient to think of the component. Alright, and then we apply another 90-degree pulse, let us say at the spin A at the moment. Then what that will do, that will turn this blue and the green vectors in the z direction with a plus z and a minus z. And this is of course an interesting state. We have created the state of the spin A, which is different from the initial state, where in the initial state both of the magnetization was pointing up. Here one is pointing up, the other is pointing down. And this is an interesting state. We call it the magnetization of the A anti-phase with respect to B or X, or whatever it is coupled to. But we'll come to that later. And at this point, if we are now apply the 90-degree pulse along the y-axis on the spin B that it is coupled to, in a homonuclear case, these two pulses are simultaneous. And I have therefore written here in this as the 90-degree pulse which acts both on spin A and B. But I can think of them as one after the other because actually they commute. Okay, then we will measure this state of the spin A as plus half and minus half. And if this time, suppose I looked at the spectrum, it would look like the following. Oh, I'm so sorry, I wrote down it wrong. This will be the B, and this will be the A. Oh, it is right. Yeah, it has become actually a B magnetization at this point. So the B magnetization is pointing up and down, while the A magnetization remains, it's correct. What I had drawn here is okay. And this is then gives rise to what's called a diagonal peak. This gives rise to the cross peak. And this is one way of saying that A magnetization has been transferred to B magnetization. Okay. Well, this picture is okay. It's very illustrative too, except that it's all right for single quantum transitions or coherences and for weak coupling. The proper way of looking at what is happening to the spins is really through the help of the density matrix. And I will briefly go through this and see how one can follow that. The signal in time domain T2 as function of T1 and T2 is given by the trace of this quantity. What is this quantity? This is the state of the spin system at this point, immediately after the first pulse, Ix, because I have a 90-degree Y pulse, and this has, Ix operator has the magnetization of spin A, B, C, D, everything. Okay, it has all. It is sum over I, Izi, all the spins are included in this. Then they evolve during T1 under our coupling Hamiltonian, and then we apply a pulse, P, we designate the action of this pulse by an operator P, and then they evolve in a Hamiltonian H2, and then we detect with the Ix operator. And other side I have just written the unitary transform of those. And therefore what we have here, this we have done again in lecture number 2 quite in detail, is that this consists of a two-dimensional time domain data which has a frequency omega KL in T2, a frequency omega NM in T1 of amplitude ZKL MN, which is given by this matrix element. All right. Now let's see what we get when we try to go further. Here what I have written down is this is a weakly coupled two-spin system. The eigenstates. The eigenstates of the system are, both the spins are up, alpha, alpha. One is up, the other is down, alpha, beta. The first one is up, down, the second one is up, beta, alpha, and beta, beta. And their energies are given here. It is rather straightforward to calculate. I don't want to go through the calculation of the energies, but they're given here. And if you look at the energy level system, it gives 4 energy levels, and which has 2 A transitions having frequency nu A plus minus half J, and has X which has a frequency nu X plus minus half J. And this is a standard way of doing it in high resolution NMR. Then I should construct the matrices Ix and Px. Ix matrix, now I am thinking of two spins, consists of sum of Ixa plus Ixx, where A and X labels are on the spin, and X is the X component. All right, I mean, this is, I've written down straightforward, but one can see how it's constructed. If you just have to see, suppose we have a one spin system, and we have spin up and down, then we have this matrix which says this is between state 1 and 1, and this, there is no change in magnetic quantum number, so it's 0. Ix has 0 element on that. But if when these two states are connected, that is plus minus 1, then it has a 1. So wherever there is a plus minus 1 difference between the total values of magnetization, you can write 1 here and 1 here. And then you have to do it for two spin systems. And if you do it for two spin system, then you see the states are alpha, 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 beta, beta, alpha, and beta, beta. And for spin A, the matrix is this. Wherever A spin flips, you put a 1. Wherever X spin flips, you put 1 on that element. And then add these two. If you add these two, you get this Ix matrix. Now we have to calculate this Px. The Px is a little more complicated. Okay, Ix is easy to calculate, and we see that what is Px is e to the power minus I pi by 2 Ix. And I can write it as e to the power minus I pi by 2 Ixa into e to the power minus pi by 2 Ixx, because Ixa commutes with Ixx. And then what I'm not going to prove but use is this quantity that I should have written down separately, that e to the power minus I pi by 2 Ix of A for spin half. One can show that this is equal to cosine pi by 4 unit operator minus 2I sine pi by 4 Ixa. And when pi by 4 I put it down, it's 1 upon root 2 unit operator minus twice Ix of A. And I use it twice. When I use it twice, I get the Px operator as given by in the denominator. And then I substitute the value of Ixa and Ixx from the previous expressions that I had, and I get Px operator, and I can construct the Px inverse. That's all what I have to do to calculate the total spectrum. How the Ix matrix and the Px matrix. Once I have the Ix matrix and the Px matrix and the Px inverse matrix, then I just have to calculate the matrix elements. And let's go through that. Okay, I want to calculate Z1212. That is, so I will have Ix12, which is 1, Px21, which is minus I, then Ix12, again 1, Px inverse to 1, and that's plus 1 to 1. And so when I multiply, I got 1, 2, 1, 2 as 1. Similarly, you can go through and see 1, 2, 3, 4 is 1, 1, 2, 1, 3 is 1, But what I get is 1, 2, 2, 4 as minus 1. You can also verify that Z1, 2, 2, 3, which will try to relate transfer of magnetization from a transition 1, 2 to 2, 3, which is actually a 0 quantum magnetization, that it is 0. And similarly 1, 2 to 1, 4 is 0. So what it is telling us, that from 1, 2 to 2, 1 transfer has a sign 1, 1, 2 to 3, 4 has a sign 1, 1, 2 to 4, 3 has a sign 1, and on the other hand 1, 2 to 4, 2 has a sign minus 1. This is the transfer now. And the transfer from 1, 2 to 3, 2 is 0. What does that mean? That is 2, 3 is this. A 1